I'm Dan Lack. I'm a research scientist with the Cooperative Institute for Research in Environmental Sciences at the University of Colorado, and I work at the NOAA labs in Boulder as well. We've just had a paper published in the Proceedings of the National Academy of Sciences that looked at the climate impacts of the particles that come out of forest fires. Carbon dioxide in the atmosphere has a big contribution to atmospheric warming, but particles like soot and desert dust also absorb radiation and have a contribution. It's known that forest fires, when the emissions of the forest fires, that there's soot in there, what we refer to as black carbon. Very, very dark. It absorbs a lot of light. It's the most potent particle absorber we have in the atmosphere. What was the most interesting thing that we saw was that there was two other things that were absorbing at about the same level, and the first thing were these little soot particles were actually coated in oils that came out of the fire. And in a diesel engine, the combustion is so efficient that you don't get these oils, but in forest fires, the combustion isn't as good as it is in an engine. And so these oils come out and actually coated the soot particles and created what we can best describe as a magnifying glass. And so the little soot particles, which would absorb a certain amount of radiation, these magnifying glass of oil actually focused radiation in and almost doubled the amount of light that it absorbed. And the third thing that we found was that these oils were actually brown themselves. At some of the wavelengths of light, they were brown, and they were absorbing sometimes more than the black carbon or the soot itself. And so what we get from these forest fire plumes in this layer of particles is a warming effect in that layer. We'll still have some cooling at the ground, and what that does, as you can imagine, is changes the temperature profile from the ground to the cloud or to the particles. And that can change mixing, it can change how if clouds form, and it can change how rainfall might occur. I think the real significance is that we have a source of warming in the atmosphere that we haven't always accounted for. Okay, so this is the cavity ring down aerosol extinction spectrometer. And what this instrument does, it effectively measures the shadow that's cast by particles. And the way it does that is by fire a laser beam into a cavity, and there's two mirrors on either end of that cavity. And that intense laser beam bounces backwards and forwards. And without any particles in there, we can record a certain amount of light. When we put particles, for example, particles from the forest fire, when they go in there, that light disappears much quicker. And so we can get a determination of how much total light is missing, and that includes the amount of light that's absorbed and the amount of light that's scattered away. And in this system, we have three different sets of channels, and one of them measures just the particles as they are in the atmosphere. One of them measures the particles with elevated relative humidity, and one of them measures the particles after we heat them and drive off all of the semi-volatile material. So driving off the semi-volatile material with the oils that we measured, that definitely was the critical measurement in enabling us to understand the effect of the oils compared to just the soot alone. So during the Fourmile Canyon fire, we also had this instrument running, which is a photoacoustic aerosol absorption spectrometer. And what this does is measure the amount of light that is absorbed by the particles. And effectively, these particles take in that radiation and they heat up. So what we do with this instrument is draw them into little tubes. And if you think about example, an empty beer bottle, when you blow over the top of the empty beer bottle, you have a characteristic noise that comes out. These little tubes inside these cells have the same characteristic, have a characteristic frequency. And so we draw the particles in and we hit them with a laser beam, and those particles will absorb the light, and then very quickly they'll release that light as heat back to the surrounding environment. And we have sensitive little microphones that started their life as CIA microphones, and we are able to detect that noise, that heat that is coming off as a sound. We can get a really good sense of how much of the absorption is due to the soot, these little magnifying glass effect around the soot, or from the brown oils. So the photoacoustic aerosol spectrometer and the cavity ring down extinction spectrometer. These instruments were completely built from scratch inside the NOAA lab, and they're the best at what they do in the world. There's no better instruments.
So this effect that we have seen of the magnifying glass has been predicted by theory, and we've seen it in simple laboratory experiments. The fact that we can show this occurs with a source of soot and a source of oils, which is so significant as forest fires, is a really powerful confirmation of this additional warming effect. So we have a much greater detail now, so we can move forward and get an even better understanding of the climate impacts of the forest fires.